Here we have question 2 from tutorial 2. So I'm making a video of how to solve this question because I noticed that a lot of people struggled with getting started with this style of question. It involves having to sort of think about the problem for a little bit and break it down into a few steps just to make it doable. So I'm just going to walk you through this process. Okay, so what the question is asking is, if you're given an expression for the higher heating value in a dry basis, which is this expression here, so this is in terms of some numerical constants, there's C1, C2 values, and in terms of the mass fractions of the different elements on a dry basis. It's asking, if you're given this information, how would you go about converting that figure into one for the lower heating value on a wet basis? So you won't really be able to do this question unless you have an idea of what it means between high heating value and lower heating value and dry basis and wet basis. So I'll start off with HHV and LHV. So HHV you can think of as what the definition, what it stands for, is higher heating value. Basically what this means is how much heat is released during combustion if the products all return to standard conditions and the water content is in liquid form. Okay, that's a bit of a mouthful, but basically what it's saying is, if you consider some chemical reaction where you've got some sort of biomass which has some amount of carbon, some amount of hydrogen, some amount of oxygen, and you combine it with air, and you do this at standard conditions, so that's 298 Kelvin and 1 atmosphere, and you burn this, then you'll get some amount of carbon. You'll get the carbon going to the CO2, the hydrogen going to H2O, and you'll have all of the oxygen in both the fuel and the air consumed in forming the water and the carbon dioxide. So these heating values are all assuming a perfect stoichiometric balance between fuel and air. And because you've got air, you've got some amount of nitrogen left over. But anyway, the point is, you start off with some fuel and air in stoichiometric ratio, you burn it, you get your stoichiometric products, and these are returned to standard conditions. And what you're doing is, you're comparing the enthalpy before and after, and you're saying that the difference in enthalpy is the heat released, because that energy has to have gone somewhere. You start off with chemical energy in all of these bonds, you rearrange those bonds to get the product gas, but then there's a net loss of chemical energy, and that's gone to heat. And that heat is the heating value that we're talking about. So the difference between HHV and LHV is that for HHV, the water is in liquid form. For LHV, which is lower heating value, you get the H2O in vapor form. So what I'm saying there is that the difference between HHV and LHV is the state that the water is in the product composition. So if the water is still in vapor form, there is still some latent energy in that vapor water. If you allow that vapor to condense, then you release the latent energy and you get more heat, net heat, out of the reaction. So that's all the difference is between LHV and HHV, just the state of the water. In terms of dry versus wet basis, this is simply saying whether you're analysing the fuel, counting the potential presence of moisture or not. So pretty much all biomass, if you have a look at 1 unit of it, no matter where you get it from, there'll be some amount of water and some amount of dry biomass. And we know from the tutorial this week and last week that this value W, which is called the moisture content, measures how much water in kilograms there is per kilogram of wet mixture. And there's some other useful relations we can get here. So if we're saying that this wet mass, whatever it is, MW for wet, with units kilogram wet wood, whatever this is composed of the mass that's dry and the mass that's water, with units kilogram H2O. So if I divide everything through by MW, what I find is I get 1 equals MD on MW plus MH2O and MW, but that is just moisture content. Or the other way of saying this is MD over MW is 1 minus W. So if W is the moisture content, then 1 minus W is the dry wood content. And this is going to have units of kilogram dry wood per kilogram wet wood. So both this and this are useful, and they'll come up in this question. Okay, so let's go back to the original question. What are we looking for? We're looking for the lower heating value on a wet basis, but we're starting with the high heating value on a dry basis. So there's 2 things we have to take into account here. One of them is the fact that we want to move to the lower heating value rather than the high heating value, and the other one is the fact that we want to move from a dry basis to a wet basis. We could do this just in one step, but I don't think it's a very good idea. It needs to get confused. Better just to go in 2 steps. So our first goal, which is get LHV wet in terms of HHV dry, will break up into 2 tasks. First, let's account for the change between higher and lower heating values. So let's get LHV, but on a dry basis, in terms of HHV dry. And the second step will be to convert from the dry to a wet basis. So then get LHV wet in terms of LHV dry. After that, we have LHV wet in terms of HHV dry after this step, which is great, but this HHV dry term, if you remember, this in turn is expressed by these dry mass fraction values, but we need them expressed in terms of the wet mass fraction values. So the second thing we have to do is get Y, I, W, so the mass fractions for each species I, or each element I, on a wet basis, in terms of Yi dry. Then the third step is combine results from 2 into the result from 1 to get the answer. Okay, so I'll walk you through how to do this. So, part 1i. Okay, so we want to first go from HHV dry to LHV dry. So you have to think about what are the things that you have to consider in terms of what are the differences between these two values. So the way I like to approach this sort of problem, which should be solved by dimensional reasoning, that is looking at the units, is to start with the term that I'm looking for, which here is LHV dry, and write it out with its units, which here will be megajoules per kilogram dry. And then the term that we have to start with that we need to manipulate, HHV dry, and write its units out. And then to think about how this equation needs to be modified to make both intuitive and dimensional sense. So starting off, we can see that both sides have the same dimensions, so that's a good start, but clearly these things aren't equal. The lower heating value is going to be lower, so minus sign, than the higher heating value. There's some term here that accounts for an energy loss when you're going from high heating value to lower heating value. So we know that this, from what I was talking about before, is going to be due to the energy associated with the vaporization of that water in the product gas. So let's call this E subscript VAP for energy of vaporization. And the units of this, well, they have to be the same as the other two terms if you want to be able to plus and minus them. Some sort of energy of vaporization, which is a certain number of megajoules for every kilogram of the dry mass. So now we have to think about what this term should look like. Okay. So if we're talking about a vaporization energy, it's natural to assume that there's going to be some dependency on HFG. So HFG is just the enthalpy of vaporization. So this just sort of characterizes how much energy is required per kilogram of water to vaporize that water. So this is just saying you need a certain number of megajoules for every kilogram of water in order to transition it from liquid to gas state. But if we look at the units on both sides of this equation, we can see that they don't balance. So we're missing some terms here. Sometimes you'll be looking for a term, you don't really know what the name of the term is, but you have a feel for what the units need to be. So I can see, just by having dimensional consistency, I need some term, I'm going to call it x1, which will have units of kilogram H2O per kilogram dry. But I'm not really sure what this represents yet either, so I'm going to have to break it down a couple more steps. So let's just have a think about this for a second. We're looking for some term that tells you how much water is associated with the combustion of 1 unit of dry wood. Okay, so we're looking for how much water we get for every kilogram of dry wood when we burn it. So this is really going to be dependent upon two things. Some term that tells you how much water you get from every kilogram of hydrogen that's burnt, and another term that tells you how much hydrogen is in the wood. So let's explain these terms a little bit more. So X3 tells you kilogram H per kilogram dry. So this is really just the dry mass fraction that we were given in the start of the problem. So X3 is YH on a dry basis, and as units kilogram H per kilogram dry. X2, so what this term is accounting for is when you burn a kilogram of hydrogen, what is the mass of water that you get as a result? So if you think about the reaction of hydrogen going to water. And if we want to balance this, we see that we need an O and two H's to get this to balance. But what we're really interested in here is just the hydrogen and the water components. What is their mass ratio? Well, we know that chemical reaction equations give us a molar ratio, so we know that N of H, well, actually throw it the other way, we know that N of H2O over N of H here equals 1 mole of H2O over 2 moles of H. But we also know that we can express moles as, actually the other way around, we're looking for mass. We know that we can express this in terms of the mole fractions if we use the if we use the species molecular weights. So this is just NH2O, WH2O, over NH, WH. So we've already determined what this ratio is, and we can figure out easily this ratio. So this is 1 on 2 by molecular weight of this will be 18, molecular weight of this will be 1. So we see the answer is 9, and the units are kilogram H2O, kilogram H. Okay, so this is the term x2 we were looking for. So we can now go back and figure out what x1 is, and then because we know what x1 is, we know what evap is, and therefore we know what LHV dry is. So let's just do that in one go. So then we see LHV dry is HHV dry minus the mass ratio of water to hydrogen in the combustion reaction times by the mass fraction of hydrogen in the dry wood times by the latent heat of vaporization for water. So that's step 1 done. Step 2, get LHV wet from LHV dry. Okay, so here we have to think about the differences between the dry basis and the wet basis. So once again, how do we start? We start by writing the term that we're looking for on the left-hand side with its units, megajoules per kilogram wet. On the right-hand side, we have LHV dry, which will obviously be megajoules per kilogram dry. So you need to think about this a little bit before you proceed. So there are two things we have to take into account. There are two main differences in terms of the energy budget when you are burning wet or dry wood. So the two loss mechanisms that you have for wet wood is one, the fact that if you have wet wood with some amount of water, this water excludes dry wood. So what I mean is there would have been dry wood here that you could have burnt to get energy from. So the term that represents a fraction of the wet wood, which is dry wood, we have derived earlier, which is 1 minus W, with units kilogram dry per kilogram wet. So that's loss mechanism number 1. The second loss mechanism is the fact that you have to actually evaporate this water before the combustion can proceed. So there's vaporization energy cost. Okay, so to go back to where we were up here, we're going to be minus some other term, but we also see that this term here doesn't have the correct unit, so let's just write it out again. So you've got LHV wet equals LHV dry, but you're going to have some term here to convert the units, but we can see the correct term is 1 minus W. So if you just look carefully, you'll see that. So we need to multiply this by something that cancels kilogram dry and replaces it with kilogram wet, which is what this will do. Right. So this first term here, this is saying the heating value of the wet wood is the heating value of the dry wood component of the wet wood, that's this term, minus the cost of vaporizing the water. So the cost of vaporization, HFG, remember this has units megajoules per kilogram water, but we need this on a wet wood basis, not on the basis of water. So the term that we're going to need to multiply it by, if you just consider it carefully, you'll see will be W, because W is the amount of water you have per unit wet wood. So you see these two terms cancel, the units balance. So now we have LHV, W equals LHV dry, 1 minus W minus HFG W. And you should recognize this from last week. I think it was one of the questions. Anyway, that's part 2 of part 1 done. So we can combine this information to get our expression. So we have now LHV wet equals LHV dry, but we know that LHV dry is HHV dry minus the mass ratio of water to hydrogen by the dry mass fraction of hydrogen by HFG, and this is all times by 1 minus W, and then there's also another loss mechanism of HFG W. Okay, so that's the first target that we're looking for. So just something important to emphasize in this question is that this energy cost here that we're talking about, so this is from the first part, this is due to the water that is formed from the combustion. That is, the water that comes from the hydrogen and the oxygen that was in the wood and the air. This is not to do with water that was present before the combustion, because we were dealing with dry wood in that term. Important distinction. Yeah. So part 2, we can also approach with dimensional reasoning. So we want to get these yi, these mass fractions on a wet basis from mass fraction in a dry basis. So start with the same method that we had before. Sorry. Actually, I might approach this one slightly differently. So here we're looking to convert a bunch of different values. There's the oxygen mass fraction, hydrogen, carbon, a whole bunch of others, ash, from the dry basis to the wet basis. So if you think about it, when you're burning wet wood, there is two things that are really going through the process of combustion. I guess there's the wood that is actually being burnt, which goes to water and CO2. So you can see that H, O, C are involved. There will also be ash, which will be unaffected. And if there's some sulfur present, you'll also get sulfur out in the product. And you also have some nitrogen. The water component, nothing's actually happening chemically to the water. All that's happening is that it's going from a liquid to a vapor state, and then maybe back to a liquid state. I guess the point is that all that's happening is that the water is absorbing some heat and might be releasing some heat again. It's not actually changing its chemical state. But H and O also appear in the water. So when you're converting these mass fractions, O and H will have two components. C, S, N, etc. will have one component. So we'll do these first because they're a bit easier. So let's use carbon as the example. It'll be the same process for all of them. But if we want to get the mass fraction of carbon on a wet basis, remember the units are kilogram carbon per kilogram wet. We have it on a dry basis, units kilogram carbon, kilogram dry. Recall from earlier in this problem, when we're converting from a dry to a wet basis, we have this term 1 minus W, which has the units of kilogram dry per kilogram wet. So you can see these will cancel out, and we'll now have a dimensionally consistent equation, and this is simply the result we're looking for. So same for N, S, and ash. Okay. For H and O, it's a little bit different. So there is the dry wood component, which will look the same as the other species, but there's also going to be some component from the water. So if we write YH wet, which is the amount of hydrogen in the wet wood, will be the amount of hydrogen in the dry wood times by the amount of dry wood in the wet wood, which is the same as before. So just write the units down here. Kilogram dry, kilogram wet. That cancels, so that's fine. But plus sign, because there is also a H component in the water. So what is that component? Well, we know that there will be some moisture content, which will have units kilograms H2O per kilogram of wet wood. So we know that there's some term here that we're looking for, which has units kilogram of hydrogen per kilogram of H2O. So you might recognize this term because we used the reciprocal of it before when we were looking for the kilograms of H2O per kilograms of H. So you can go back and check that out. I won't take my word on it, but this will be 1 on 9 with units kilogram H2O per kilogram H. And the way you figure this out is it's just M of H over M of H2O, which is NHWH. So this W here is molecular weight, NH2O, WH2O. And these mole ratios are the mole ratios that appear in this equation. So 2 hydrogen, 1 water. So it's very similar for the oxygen component. The only difference here is going to be the mole ratio is 1 to 1 and the molecular weight ratios will be different. But it'll be a similar expression, it'll just be MO on MH2O. And the expression for this will look very similar to this. It'll just be this term which is different, because it'll be kilograms O over kilogram H2O. So I don't really have room to write all this out, but that's pretty much the solution. So then write solution line 1 and 2, and you'll have something that looks like LHV wet equals, and it'll be some function of the y values on a wet basis, w and hfg, and there'll just be some numbers in there as well, but you can sub those in. If you want to see the solution, just look up the tutorial solutions, which will be handed out sometime at the end of this week, or possibly early week 4. Right, thanks.